You're listening to Skeptoid. I'm Brian Dunning from Skeptoid.com. What really happened at Tunguska? It's come to be associated with the old thought experiment. If a tree falls in a forest and no one's around to hear it, does it make a sound? The association is not without merit. The Tunguska event is believed to have been the loudest sound ever, certainly the loudest in human history, and it was definitely in a forest with very few people around. Even the nearest settlement is some 65 kilometers away and is barely more than a village. That's Vanavara, formerly a trading post for hunters and trappers. This monstrous sound was accompanied by a series of highly destructive shock waves, which laid waste to some 2,000 square kilometers of boreal forest, leaving it a ruin of flattened, stripped tree trunks. And this all happened within the minute following what is believed to be the brightest fireball ever on Earth. An intense light that would have had every living creature's attention in the moments before the shock wave obliterated everything. The district in Siberia is a wet, swampy land in summer and a frozen subarctic icescape in the winter. The region is dominated by the large and winding Podkaimana-Tunguska River. In 1908, the entire population of this vast district consisted mainly of a few thousand people of Evenk heritage, one of some 40 ethnographically distinct peoples of the Russian Far East, plus a much smaller number of Russian homesteaders. The Evenk were semi-nomadic hunters, gatherers, and reindeer herders. On June 30th, 1908, at 7:15 in the morning, history's most violent cataclysm took place right in their midst. It's believed 3 Evenk were killed. Such was the population's sparsity. Countless Evenk were injured, some up to 500 kilometers away. Scores of survivors gave oral accounts of the event, however, which were transcribed into Russian. Most of these were collected by a Russian ethnographer at a meeting in 1926, 18 years later. Today, planetary scientists have a broadly accepted model of what happened. Note that I say it's broadly accepted, not universally accepted. And that uncertainty is largely the topic of this episode. But we'll get to that in a moment, because there are also a lot of other nominations for what could have exploded over this deserted swampland. The Russian web has plenty of wonderful information on Tunguska, and when I say wonderful, I don't mean wonderfully accurate and thorough. I mean wonderfully imaginative and fun. Much of it riffs off of a 1969 article in a Croatian journal in which the authors listed 77 possible causes for the event. 28 involved a meteor. 14 were technological. 11 involved a comet. 10 were geophysical. 8 involved antimatter. 3 were religious, and the other 3 are described as synthetic, whatever that might mean. Among these are a close pass by the comet Inca, which orbits the Sun every 3.3 years and was in the vicinity on the date of Tunguska. Perhaps it dropped us a fragment which exploded over Tunguska. A test of a nuclear bomb, which would have been a neat trick in 1908. A consequence of Nikola Tesla testing his wireless transmission of electrical power all around the world. Another neat trick, since this wouldn't have worked and Tesla never even built anything to try it with. A piece of antimatter floating through space and colliding with the Earth. 2.5 billion cubic meters of natural gas igniting. Presumably someone has calculated that's the amount it would take to cause a blast consistent with the seismic data. A collision between the Earth and a small black hole, which is interesting because the first black hole detection was made only 5 years before the article was written, so interest was likely high. An attempted communication from a presumed civilization orbiting the binary star 61 Cygni, using a high-powered laser that was accidentally too powerful. Such a beam must have had one heck of a collimator on it. A chunk of the sun that broke away and was flung toward the Earth, landing catastrophically in Tunguska. And my personal favorite, the detonation of a cloud of midges. You know how sawdust when dispersed in the air is violently explosive? Evidently, someone calculated that a swarm of midges, if sufficiently dense, could produce the same effect. They appear to have even calculated the cloud would need to measure some 5 cubic kilometers, presumably to cause a blast sufficiently large to match the seismic data. No igniting mechanism was persuasively suggested. But these are only a few of the 77. No doubt the rest of the article makes for equally colorful and entertaining reading. Today, however, we've got what's probably a more accurate picture of what happened. Our best theory was put together quite recently, in January of 2018, when a special workshop was held at NASA's Ames Research Center in California. The results were published in a freely available booklet titled Tunguska Workshop: Applying Modern Tools to Understand the 1908 Tunguska Impact. The workshop was attended, in person or remotely, by some 52 international experts on Tunguska, with the goal of establishing a synthesis of all the expert findings. This meeting, and the refined model of Tunguska, was made possible by a relatively new development in the field: the 2013 event over Chelyabinsk, Russia. The Chelyabinsk event was a large meteor that streaked into the sky one day and exploded violently, causing vast damage and some 1,500 injuries, mostly from things like broken glass. But the Chelyabinsk event was not just documented on Twitter and YouTube. Because it happened in modern times, substantial data was collected, and it was able to be thoroughly characterized. It gave us a lot of data that helped us, in effect, reverse engineer what happened at Tunguska. We had computer models before, but Chelyabinsk allowed us to refine and calibrate those models to be much more accurate. The 2018 workshop was the result of these new models being applied by scientists all around the world. Chelyabinsk was a rocky meteor some 20 meters in diameter and weighing some 12,000 tons. Heat and aerodynamic forces caused it to explode. And an explosion like that generates a shock wave which, if it's large enough and close enough to the ground, can destroy structures and trees and other things on the surface. Chelyabinsk exploded with a force roughly equivalent to 500 kilotons of TNT. By contrast, the Tunguska event was much larger. It was probably in the range of 50 to 80 meters in diameter, and exploded with a yield of 10 to 20 megatons, 20 to 40 times that of Chelyabinsk. Additionally, Tunguska came in faster and exploded closer to the ground than did Chelyabinsk, only about 10 kilometers up compared to 30 kilometers for Chelyabinsk, thus the greater damage over a larger area. If you watched Chelyabinsk on YouTube, magnify everything about it many times, and that was Tunguska. But the improved models are not the only way we can tell what happened, because Tunguska also left us multiple lines of evidence. The first of these is the pattern of trees that were flattened. Any photos you've seen of Tunguska are likely black and white pictures of a lot of flattened tree trunks. Mostly, the trunks shown in the photos are stripped clean of leaves. This is because the thermal radiation from the blast was hot enough to set them on fire, but also because the photos weren't taken until 1927, when Russian mineralogist Leonid Kulik led the first scientific expedition into the blast zone. Trees in the center were burned and dead, but still standing upright, in a circle 8 kilometers across, because the explosion happened directly above them. Further from the center, they were knocked flat in an outward direction, in a giant butterfly shape 70 kilometers wide and 55 kilometers long. That butterfly shape of the blast pattern, which has been reproduced in the lab, is consistent with an explosion moving laterally downward at an angle of about 30 degrees from the ground, and the varying speed and pressure of the shock wave produced as the exploding object moves along that path. The second line of evidence is the seismic and barometric recordings of the event taken all around the world. In 1934, a paper in the Quarterly Journal of the Royal Meteorological Society listed many of these. Seismic readings taken from all over Eurasia indicated that Tunguska experienced a 5.0 earthquake from the shockwave. Not bad when the blast was 10 kilometers overhead. The barometric impact of the shockwave was recorded nearly everywhere as an atmospheric pressure wave of infrasound, even as far away as Washington, D.C., on the other side of the planet. Third, we have the eyewitness reports. These described something very similar to what we see in the videos of the Chelyabinsk event. They included casualties and numerous burns from the thermal radiation. Furthermore, it's a historical fact that for several nights throughout Eurasia, the night sky was illuminated, consistent with the upper atmosphere ice crystals that would be expected to be created from an explosion of this magnitude. Some photographers were even able to take pictures by the glow from the night sky. But all this isn't to claim that everything is known for a fact. All of these parameters for the Tunguska object are probabilities. This standard model is what best fits the data. The best known alternative is that it was a comet, not a meteor, which, if we tweak some of the parameters, can also be made to fit the data, just not as well and with lower probability. For example, a comet has much lower strength than a rocky meteor and would not have been able to penetrate as far into the dense atmosphere before breaking up. Some parameters, like whether the meteor was carbonaceous or chondritic, don't affect the model very much, meaning it's more difficult for us to know what it was made of. It's noteworthy that no meteorite fragments have been recovered at Tunguska, which some have pointed to as evidence that it was a comet or something else. However, it's not too surprising. Of Chelyabinsk's 12,000 tons, less than 1 ton in total was ever found. Less than 1% of 1%. And no impact craters were produced, as the fragments fell at a relatively slow terminal velocity. Though Tunguska was larger, its fragments would have landed in soft, boggy ground and would be extremely difficult to find. A few large circular depressions were identified by Kulik's 1927 expedition and first taken to be impact craters, but today it's accepted that these are thermokarsts, features caused by the melting and thawing of permafrost. The question of what exploded over Tunguska in 1908 is another case where it's important for us to be mindful of the scope of uncertainty. Too often, when we acknowledge that there are unknowns about some phenomenon, many interpret this to mean we know nothing about it at all, and it's just as likely to have been aliens or a cloud of midges. The scope of uncertainty surrounding the Tunguska event covers many aspects of it, but all are confined to a narrow range of possibilities. Similarly, when we point out that this standard model is only the most probable, that doesn't mean that Tesla's free energy machine is equally probable. When you diverge even a small amount from the standard model we've described, the probabilities drop off rapidly and approach zero. So when we ask what really happened at Tunguska, we are within the bounds of accuracy, to any practical degree, to confidently assert that it was the entry and explosion of a hypersonic superbolide, many times the size and with many times the energy of the similar Chelyabinsk event. Even though we don't know everything, we do know that. A great big Skeptoid shout-out to premium members Terry McGrath, the very grateful Selena O'Brien, Dr. Stranger, Lori Seraphin, and Tamazon. Becoming a premium member is the best way to enjoy Skeptoid. Not only do you get a special podcast feed with more than 10 times as many episodes, all ad-free, you can also get the nifty Skeptoid USB 3.0 flash drive, preloaded with all the podcasts and movies we've ever produced. It's easy to get. Just come to Skeptoid.com and click Go Premium. And if you're a student or teacher, don't forget our student question episodes. Record any question, and I'll play it and answer it for you right here in a special episode. Come to Skeptoid.com and click on Student Questions. You're listening to Skeptoid, a listener-supported program. I'm Brian Dunning from Skeptoid.com.